Good morning, everyone, and welcome to Deep Learning for Data Scientists using Apache MXNet and R on Amazon Web Services. My name is Dan Banga. I am a business development manager for Amazon AI, focused on machine learning and deep learning engines. And today with me is Jared Lander, Chief Data Scientist at Lander Analytics. Jared, do you want to introduce yourself real quick?
Hello, thank you for having me. As Dan said, I'm Chief Data Scientist at Lander Analytics. I'm also the organizer of the New York Open Statistical Programming Meetup, the world's largest R meetup, as well as the New York R Conference. I'm an adjunct professor at Columbia University, and I'm the author of the book R for Everyone.
Thank you, Jared. So today we are going to cover rapidly the strategy of AI at Amazon Web Services with a focus on AI engines and then cloud GPUs as the utility compute. We're also going to cover MXNet fundamentals, essentially the benefits and the introduction of MXNet API. And going forward, we are going to talk about how R works on MXNet with a walkthrough logistic regression using MXNet and R together. So this is essentially the last slide, and this is the takeaway that you have to take from this presentation. So AI in short terms, what is it? Well, the way we see artificial intelligence is essentially a combination of hardware and learning algorithms working together in order to accelerate the process that humans typically take in order to complete a certain task. So we see machine learning as a subset of artificial intelligence, which is essentially taking advantage of a certain probabilistic and mathematical methods in order to fit a function on top of a certain data set. And deep learning takes to a further level the concept of machine learning, essentially neural networks within machine learning in order to fit a network structure on a data set. And when you look at the deep learning network structure that is leveraged now in the form of neural nets, you can see that it has essentially the structure of multiple neurons working together, and that inherent structure of deep learning networks makes it highly parallelizable, and it makes it a good candidate for GPUs. We're going to talk about that in a bit more, in a little more time. So these are a few use cases of deep learning at Amazon. We use deep learning for applied research, core research, advertising, machine translation, robotics, and then a lot of computer vision with natural language processing, natural language understanding. There's a lot of deep learning happening at Amazon, and our customers as well on Amazon Web Services use deep learning for genomic processing, modeling and simulation, recommender system, and natural language processing. So in the past few years, there has been a massive revolution with the competencies that people can inject in their applications or their workflows leveraging deep learning. And AWS is there to enable that by providing high-performance compute in the form of GPUs without P2 instances and more. This is an example of a customer called TuSimple, based in China, that essentially does computer vision using Apache MXNet on R and training their models with GPUs on AWS. This is an example of another customer in New York called TuSense that essentially does behavioral biometrics by capturing behavioral data on their users as they use their applications in order to come up with a fingerprint or an identity of their customers, and being able to tell whether a certain action is initiated by the customer or not natively. This is another example of a typical image classification app running on Shiny and R, and essentially loading a pre-trained model within the R interface and exposing that with the web UI with Shiny and enabling people to classify images using their browsers. So deep learning is for everyone, and that's essentially our goal at AWS. And the drivers for deep learning for everyone are essentially fast compute, ubiquitous data in the form of sensors, Facebook, Instagram, and every users nowadays generate a certain data artifact that could be leveraged for deep learning. And the advancement in learning algorithms as well in the form of machine learning and deep neural network makes it possible to get to that intersection of compute data and advanced learning algorithm that enable people to process deep learning algorithms faster. Our strategy at Amazon Web Services is to democratize artificial intelligence. We have a layered approach. We start with services where we pre-train deep learning models and make them available for people like you and I to just use without having to go through the headache of training model yourself. So this is geared towards developers that just want to use a service, and that service has to be AI powered or AI enabled. The second layer of our approach is essentially providing a platform that enables practitioners that have the capability to train networks or to train machine learning algorithms to do it themselves, leveraging our compute and platform layer. So it comes in the form of Amazon Elastic MapReduce, Spark and Spark ML running on Elastic MapReduce, or Amazon Machine Learning, our predictions as a service platform. And underneath that surface, we have what we call AI engines in the current form of a pre-trained, of a pre-built image artifact that is enabled with most of the popular deep learning framework like Apache MXNet, TensorFlow, Caffe, Torch, Llano, CNTK, and more coming down the line in 2017. So we make this infrastructure available for you so that you don't have to worry about the operational challenge that comes up with putting this infrastructure together. And underneath that, we have the hardware surface where customers like you can leverage GPU capable infrastructure in order to train your deep learning models faster. So from a large non-demand variety of compute, we right now have what we call the P2 instances that are Kepler enabled with K80s, and in which you can have up to 40,000 cores of CUDA cores. But we pre-announced what we call our P3 compute families, which are enabled with Volta V100, the fastest NVIDIA Volta-enabled GPU chips that will be released around Q3 or Q4 this year. To talk about Apache MXNet rapidly, the reason we chose Apache MXNet as a platform for as a deep learning library is for essentially three major reasons. It's flexible. Many deep learning infrastructure, deep learning libraries come up with a certain programming language that it sort of oblige you to use. Our approach is to serve the maximum capability, the maximum number of customers possible, and we want you to be able to use your language of choice in order to use Apache MXNet, and that's a benefit that comes with it. The portability of MXNet, in the sense that it's a lightweight library, is also a value proposition. It's also a reason why we chose it as a framework. Essentially, you can train the model at scale on the cloud and run it on a lightweight infrastructure like a drone or a mobile phone or browser. It's also high performance. You can scale an MXNet training model on multiple GPUs within the same machine, or multiple GPUs within multiple machines. It's also the most open platform available on the Apache Incubator as of now, and it runs best on AWS with the full integration with GPUs and the optimization that our engineering teams is putting into the platform in order to make it work seamlessly with other AWS services. Apache MXNet scales almost linearly, close to 91% efficiency. And this is useful when you want to run a multi-cluster, multi-GPU environment, because it enables you to not lose too much on cluster management operations and still generate a close enough accuracy that you would have with a linearly scalable environment. With MXNet, you can train a scale in the cloud and then deploy on a browser or a mobile device. And so it's big in the sense that it can run at scale on the cloud, and it's also small in the sense that it can run on a mobile device. So going forward, our tools for enabling people like you and myself to run deep learning models at scale in the cloud come in the form of P2 instances. Like I said earlier, up to 40,000 CUDA cores. A deep learning AMI that is a pre-packaged environment with all these popular deep learning frameworks that enable you to run models faster or to train and build models faster. And a CloudFormation template that enables you to launch a cluster of these deep learning AMIs together and get started faster. So I'll hand over to Jared to sort of quickly introduce us to R and MXNet before we walk you through a sample code.
So MXNet is the deep learning framework that is the one of choice for R users. So as many people know, R is an open source statistical programming language. It is meant for data, for statistics, for machine learning, for data science, AI, whatever word you want to call it. See, there's a big ecosystem all around R. It is an open source community. The Meetup in New York has over 8,000 members. There are meetups all around the world, in Singapore, in London, in Tel Aviv, in Cleveland, in San Francisco. You name it, there's usually an R meetup. And it's a community of people who really love the language and support it and have written more and more packages. In fact, there are 10,000 user-contributed packages in the R ecosystem.
So, Jared, tell us a little more about the origins of R.
So, there's a language called S. It was created by John Chambers at Bell Labs, and it was meant for statistical computing back starting in 1976. And out of that grew R, which was written initially by Robert Gentleman and Rossi Haka. Some people ask why it's called R, and usually there's some pun that it came out of S, and R is the letter that comes before S. But if you also notice, it is Robert and Ross's first initial. It's very powerful for statistics. You can do your traditional statistics that you learned in your college stats class. But of course, for advanced modeling, whether that's a linear model, logistic model, Poisson regression, and of course machine learning, however you like to define that, if that's highly penalized regression, if it's decision trees, if it's clustering, it's great for machine learning. And of course, it's graphics. R has long been well known for its graphic capability.
So why is R one of the favorite tools for data scientists?
Because it was really designed with data in mind. Its canonical data set is a data frame, which is a rectangular data store where the rows are observations and the columns are variables, and it has mixed types. Each column could be a different type of data. And this really allows you to express data the way it exists in the real world. It makes it so natural for a statistician.
How does that compare to the other tools for data science, like Python and Anaconda?
So one of the things that allowed Python to start doing data science was when Pandas introduced the data frame. And so the Pandas data frame is a natural homage to the R data frame. And that data frame is really what started making it so powerful. But the big difference between the two languages is their syntax. Python is a language where if you're an engineer, it helps you think that way. R is a language where if you're a statistician, a mathematician, you think that way. So it's a different way of thinking about programming.
Okay. So, and then R is also possible to use for deep learning, essentially.
Absolutely. R has long had a neural net function built right into base R. It's the MNet package, been there for decades. But now, of course, there's all these other newer deep learning packages, specifically MXNet.
So why did you think that MXNet is a deep learning framework of choice for R? Why that statement?
It is a tool that allows you to build symbolic neural networks. It allows you to build them up symbolically, layer by layer, sort of in a fashion similar to ggplot, where people would build up graphs layer by layer. So it's a natural way of thinking, and allows you to do this in a nice, simple way that makes sense, and you can follow the computational graph as you build it. And it's something that's amazing. A lot of people say you can't do deep learning in R, but clearly, as this slide shows, you absolutely can do it in R. It is a way of building it, whether it's on CPU or GPU, using the same symbolic graph. So it's a nice, powerful way to do deep learning in R.
Okay. So at this moment, we are going to walk through a sample code in which we do logistic regression, which is a typical machine learning, probabilistic machine learning algorithm, and we will do the same thing with R and MXNet. And Jared is going to walk us through the code and explain what we're doing. Go ahead, Jared.
Wonderful. So this is an HTML document generated by R Markdown, so it's fully reproducible, and this will be posted online. First, we're just looking at some of the packages we'll be using. Of course, Migrator for the pipes, metrics for calculating log loss, and MXNet, of course, for the fitting. And there's other packages here for data manipulation and for plotting. You can scroll through this and see all the different packages we used to make this helpful for us.
So I see HGBoost here. Can you talk to us about HGBoost a bit?
Yeah, so HGBoost is a package created by DMLC, which are the same people who brought us MXNet. It's a package mainly used for fitting boosted decision trees, but it could be also used for boosted linear models and for fitting a variant of random forest. So we're going to use XGBoost to fit a random forest.
And XGBoost has won a lot of Kaggle competitions lately.
Yes, it has. In fact, up until deep learning became such a powerful force, XGBoost was just about always the winner in all these Kaggle competitions because it fits amazing models with great speed and very high accuracy.
And it was built by the same team that built MXNet.
Same team as the MXNet team. So they're winning a lot of hearts.
Awesome. So talk to us about the data that we're going to analyze today.
So the sample data we have is from the New York City Department of Planning, and it is about tax lots in New York City. So you have a parcel of land, And that, of course, has a value connected to it, and it's all this descriptive information. And as we can see here in the data table we built, it's the type of fire department, whether that's a hook, a ladder, an engine, if it's what type of zoning it has. And there could be multiple zoning districts. If it's a retail, a public, or mixed use, what type of land it is. And you can see there's many, many columns. There's dozens of columns here.
What are we trying to predict?
We are trying to predict whether the value of the land is considered high. How do we determine what's considered high? We chose the median value of the land around $680,000 for a parcel of land. We want to predict whether or not the land is above that value or below.
So, and that's what we're looking at here in the bands and the classes. Can you explain this, Chad?
Yeah, so when you're doing logistic regression, you are concerned about class balance. You want to have, it would be nice to have them, if not equal, closer to equal. And we can see here that for our train, validate, and test data sets, they're about the same proportion, about 2 to 1, which is something we can work with these models.
Okay. And then you use VTreat to treat the data set.
Yes, so VTreat is a package that is meant for feature engineering in an automated way. This way we don't have to spend lots of time doing it. So first thing we do is to tell it which variable is the one we're looking at, what its target is, and then we use design treatment C because we're doing a classification problem. And as you can see here, it goes through and works on the design matrix for all these different variables.
So how much effort would it take typically if you had to do this yourself, treating the data manually?
Depending on the problem, this can go for minutes to hours to days to weeks. It's a very complicated part of the process. And in fact, Andrew Ng even said that applied machine learning is basically feature engineering. So this is helping doing a lot of that for us.
So in order to pass data into what we call here feed-forward network, which is the neural network part of this exercise, there is a good deal of preparing the data and putting that into matrices. Can you talk a little more about that?
Yes. So traditional R modeling functions use a data frame and then a formula interface. And this actually won many statistical computing awards for its flexibility. However, a lot of the more modern packages require you to have an input matrix and an output vector, or a matrix itself. And so we're preparing those ahead of time. And if you follow developments in the R community, such as the creator of the Carrot package, Max Kuhn, he's working on a new package called Recipes to make working with formulas easier and to get to these X and Y matrices.
So it's interesting that you're talking about packages. So as of now, we have VTreat, we have Carrot, we have a number of other packages that are used. It sounds like the R ecosystem is full of packages that facilitate the process of data science. Is there a benefit for MXNet to be part of that packages family?
Absolutely. So R has been around since the 90s and since the 70s if you count S. Is that this whole community building these add-on packages. And these are usually research professors designing new algorithms, new methods, and allowing MXNet to tap into this whole ecosystem of data science that's been building for decades really lets you combine the best of data manipulation, visualization, modeling, and reporting that you get this great synergy, to use that word, brings it all together.
Awesome. So at this point, you're creating helper functions. Can you tell us what you're doing here?
Yes, so when you're using MXNet, you can define your own loss function. And since we're doing binary regression, we're going to use the log loss function. So we're essentially just wrapping the log loss from the metrics package into a function that MXNet knows how to use.
And it's interesting that you're creating a custom MXNet metric. That means the framework allows you to extend it and add new metrics.
Yes, it allows you all the flexibility to pretty much do what you want with it. And that's one of the beautiful things that R has always done. You can always write anything you can imagine.
Okay, so at this point you're creating a network. What are you doing here?
So this is the crux of the modeling. We're not fitting a model yet, we're designing the computational graph. We're building it up layer by layer. And this is really conducive to the piping system introduced to R by Magritte. It's really nice at allowing the flow to go so you can see how one function feeds into the next as you build up your layers.
That's interesting because when you typically see a deep learning network being created with Python, you see multiple variables being created. But at this point, you have only one net variable and you pipe everything going forward to essentially have a chain of operations or computational graph built in this single variable.
And it makes it so much easier to read now.
Yeah. Right. So, and then you have dropout and batch normalization going on here. Can you talk to us about that?
So let's see how this thing starts. We start with our data set. And the very first thing we do is drop out. We drop out 20% of the predictors. This is a form of regularization to reduce the capacity of the model. And you might be saying, well, why do you want to reduce capacity? Isn't that bad? Well, having too much capacity is bad too because you could be overfitting. So we're going to randomly drop 20%.
Okay.
We then feed that into a fully connected network. And this is the 256 nodes in our first hidden layer that is created by multiplying the remaining input variables by a weight matrix W plus a vector of biases.
Okay.
We take that, then we batch normalize. And batch normalization essentially makes each of these hidden units have 0 mean and standard deviation of 1.
Why is that important?
So when you're computing through backpropagation the gradient, it's computing a gradient for each hidden unit, assuming all their hidden units stay constant. Well, that's a nice simplifying idea. Doesn't actually represent reality. That could lead to problems. So by batch normalizing, you can take that into account and fix that error.
Okay, and then you activate.
Yeah, so then after you have your hidden units and they have been normalized, you need to activate them, typically with a nonlinear function, because otherwise you're just building essentially a linear model and things don't learn as well. So we're using the rectified linear unit as our activation function to propel these units into the next hidden layer.
And essentially you go through the same process over again for a second layer before you fully connect in the end and have a logistic regression output layer. Can you talk about that?
Yeah, so the more layers you have, the deeper it gets. The individual layers don't need to be as wide, and that makes the fitting process easier. So you can go deeper and deeper, and that actually makes it easier to fit than having just one wide layer. Then we get to the end and we have one hidden unit because it's binary regression. You're just predicting the probability of it being true. And the output is a logistic regression output. If you do deep learning, this is called a sigmoid output. For you coming from data science and statistics, you call it inverse logit.
Okay, so we're doing logistic regressions with a deep learning library. What's the benefit or the drawback from doing that?
So the benefits could be you could fit more, I guess, nonlinear relationships. Of course, logistic regression is a form of generalized linear models. There's that word linear in there. By doing deep learning, you're able to capture these other relationships. Now, of course, one drawback is doing statistical inference. It's oftentimes you don't know what's happening.
Okay, so now we look at the network weights and then we visualize the network.
And this is a nice function, graph.viz, come from MXNet, which lets you see each layer of the network you have built as a symbol. And it's built with the diagramr package, which is an HTML widgets package that produces JavaScript that can naturally embed into an HTML document.
So you can put it in your website.
Absolutely, and you can even put it in a PDF by using the web shop package.
So at this point, we haven't passed any data to the network. We're just designing it. And what are we doing now in the network training part of the code?
So first, I'm actually setting an environment variable because I did this on my laptop. Deep learning is great for running on a GPU, but I wanted to run on my laptop just to see how I could do things like everything else. I have 4 logical threads, so I set the environment variable to use all 4 of them. And then we set the random seed for reproducibility. Then we get to the function mx.model.feedforward.create. This is where you actually kick off the training. The first argument is the symbol we built, the computational graph. And then we supply the x and y matrices, our predictors and our response. You can choose the optimizer you use. There's stochastic gradient descent, there's RMS prop. We're using Atom because it uses optimization that takes into account momentum, which helps you just get a better fit.
Okay.
We provide validation data to make sure we're doing it well. And here, this is very important. CTX equals mx.cpu. I'm fitting this on my local laptop. It's a little 12 gig, 13-inch laptop, nothing that impressive. And it's simple. If I wanted to switch to GPU, you simply change that to mx.gpu. You literally change one letter. And then in the parentheses, you have multiple GPUs. You can say which one to use or use multiple GPUs.
What if I had multiple GPUs? Do I pass a list?
So you actually pass in a key value store, which is in R, essentially a list. And you can create that in the earlier data step. And that key value pairs tells it which set of data to go to which GPU.
Awesome. And at this point, we're doing predictions. This is the actual prediction.
That's predictions. Just like every other R modeling function, all you need to do is call predict. Give it the model, give it your new data, and it predicts it for you. And it's that simple.
So if I knew how to predict from any type of models in R before, I can use MXNet, use the same syntax, and have predictions going on the way it happened before.
Same thing. It uses the R S3 object notation. It's all automatic, just like you're used to.
Okay, and that generates an array or a vector that you transpose here.
Depending on what type of prediction you're doing, it could be a vector or a matrix or an array. It depends on if you're doing multi-class classification, binary, or regression. They come in essentially an extension of an R vector.
Okay, so for fun, we decided to compare the performances, or to compare R with MXNet with other libraries that are out there. Can you talk a little bit about ElasticNet and HGBoost?
So ElasticNet was for a long time one of the greatest innovations in machine learning. It still is. It does penalized regression, both L1 and L2, or lasso and ridge, depending on your field, and it fits a generalized linear model on the data in this one line of code. And then for the predictions, just like everything else we've seen, you call predict, and you pass in new data, and you get your predictions. HGBoost is typically used for fitting a boosted tree. However, with certain parameters, such as subsample and call sample by tree, you can make it fit a random forest. So it's just a new, fast way of fitting random forests. So it's really nifty. And again, predictions, just as simple, use the predict function.
So again, you can be working on a problem and have 2 or 3 or 5 different solutions that you're exploring, and within the R and MXNet environment, you're essentially using the same syntax to fit your models.
Yep, and it becomes even more seamless when you use Caret, because then Caret exposes a just standard API that calls them automatically. And when we fit these things, the prediction was all the same. When we fit all the models that had slightly little differences, you use Caret and it becomes even more seamless.
And then we tried to use support vector machines. What happened here?
It just ran and ran and ran and ran, never converged, and my computer wasn't happy, so I decided it was just not going to happen. And honestly, when you have all these other tools, I'm more than happy with XGBoost, GlimNet, and MXNet.
Okay. Now, for the discussion part, let's look at performances here. So can you tell us what ROC is and then what we are looking at here?
Yes, it's the receiver operator characteristic. It gives you a sense of how good your model is doing. When it comes down to it, essentially, you want your curves to be as close to the upper left-hand corner as possible. The closer they are there, the better your model is doing.
Okay, on the data set.
On the data set, in this case on a test data set.
Okay, and then you have to make sure you choose the right model for the right problem.
Yes.
So can you tell us about the sensitivity and specificity performances on the data set that we analyzed today?
So in our data set, all the models, as you can see here, did roughly comparable with each other. You can see we have this nice interactive graph that we could hover over, and we can see them how they're all very similar. So in this case, for a very simple logistic regression, this actually is a very simple data set. It fits nicely almost no matter what tool you throw at it. They all do roughly the same. So in this data set, you're not going to go wrong too easily. You can't go wrong that much.
So there are many ways to solve a problem. Mm-hmm. And what would be your advice to folks that want to engage in, doing deep learning with R overall, with all the packages and tools that are available to them, including MXNet now and deep learning?
So you want to know when to apply it, when it's worth your time. Deep learning is an amazing new tool, but it isn't the only tool. There's a great quote in the deep learning book that says there is no free lunch, right? You can't just use one tool for everything, so you need to know when to use it. So you need to build up your domain knowledge when to use it. But then when you decided upon doing deep learning and you're going to use MXNet, learn about how you build up that computational graph. When you do a dropout, when you do batch normalization, when you should use a ReLU versus a tanh versus a sigmoid, when to know what order to put them in. So it's very important to get that theoretical understanding of what's happening in a deep net. Don't just go blindly apply the tool. Look into the research, read about it, and apply the correct model for the correct instance.
And try it with 2 or 3 other tools and compare. Always.
Absolutely. You always got to compare your machine learning AI methods.
So in summary, here we have used a deep learning library called MXNet in the R ecosystem seamlessly with the syntax that typical R users would be used to, and essentially train a deep learning model on a sample data set. But deep learning is also useful in image analysis and other frameworks. So what is the real benefit here? Dropped out for a second.
So we're talking about image classification using MXNet.
Right.
And MXNet lets you use the whole family of deep learning models, including convolutional neural networks, which have been shown to be great for image classification. And it allows you to not just build your own, train your own on scale on as many GPUs as you'd want. If you have the new P3 instance on Amazon, that's Volta, you said.
Yeah.
And unless you train it on many, many cores, and these are fast cores, you can actually start with pre-trained models. MXNet provides a number of trained models such as ResNet, AlexNet, I believe ImageNet, and a few others. You could start with those, and then if you want to fine-tune it, keep training new examples. And now you have these weights that already were pre-built, you added your own, and you can very quickly classify images with minimum startup time.
All that within your native R environment that you're used to.
Yes, you've been used to using R this whole time, you can keep using it.
Thank you, Jared. So at this point, we are going to take questions. I will stop sharing my screen and get back to the presentation. So this is a short link for resources page that you can get to and get more information about MXNet and how to get started. We will augment these resources set with the deck and the code walkthrough. Thank you. So we'll take questions now.